Okay, so today I want to give you, now that we've collected a bunch of IR and you kind of know what they look like. Shh. Hey, you two. Hush.
Sorry.
Not you. Those two. Again. And you two. Shh. Should I start that recording over? All right, so now that you've seen a bunch of IR, you've collected some, we're going to talk a little bit about how you need to be analyzing them for this class, okay? Next semester it'll be a little bit different. Next semester you'll have unknowns. You have to analyze them for the unknowns. This semester you may get an unknown or two, but we'll see. I haven't worked out all the labs we're doing this semester. I'm writing a couple of new ones, and so we'll see how that goes. All right, so start with spectroscopy. Involves the interaction of light and matter. And in spectroscopy techniques, we either measure the light that is absorbed or the energy that's emitted once the light is absorbed. Okay, now by light, what do I mean? Waves, right? And they come in packets we call photons. And when light energy comes in, it interacts with matter. It has to be, the photon has to be absorbed somehow. If it's not absorbed and it passes straight through, we get no information other than it doesn't absorb that photon. Okay? But the light has to be absorbed. Now, from your vast knowledge of the Bohr model, what is the Bohr model? Planetary model, like the nucleus and then the rings, right? And the electrons are in these orbits, right? That's all we need for this. We don't have to do the quantum model, really, for this stuff. From your vast knowledge of the Bohr model, when a photon is absorbed, what happens to the atom? Moves up in an energy state. What moves, though, in that case? An electron, right? Remember, the electron moves to a higher energy level. And then when the electron drops back down, what happens? Shoots a photon out, or it can emit it as heat. Okay, so there's all kinds of things that could happen. Sometimes the energy gets transferred. Those are really neat reactions when you shoot in one color of light and a different color of light comes out. Hopefully I'll get to show you this sometime. I haven't planned to do this lab, but if you ever get a chance to extract chlorophyll, chlorophyll will absorb light and emit it in the red, because normally it emits red light, but if you give it ultraviolet light, it will actually emit red light. It's creepy. It looks like blood. Like you have these little green vials and you stick them in a black light source and they turn like blood red. Yeah, so if we have some spinach in the freezer, maybe I'll show you that. It's kind of a fun, just kind of gee whiz thing. Okay, so yeah, same thing that as yesterday. So light comes in as a photon, packet of energy, absorbed by an atom in the Bohr model, and then it's re-emitted as light or heat or some sort of thing. Okay. Generally speaking, that's what happens. Now, in molecules, it turns out energy levels are quantized in molecules too. So you could be looking at electron transitions in molecular orbitals, or you could be looking at vibrational energy. So like if I took a string and I vibrated it, right, it could only sustain certain frequencies that are what we call harmonics or resonant frequencies of the string. So like a guitar string. You guys familiar with how a guitar string works, right? It's strung between two hard points, and when you pluck it, you either get full waves or you get harmonics of that wave. So if you've ever heard somebody play guitar, I should have brought my guitar in. And you put your finger halfway down the neck of the guitar and you pluck it, you get the harmonic of that wave. It's actually twice the frequency of that wave. You can put it at a third, and then you get a third. You get 3 times the fundamental frequency. Put it at a fourth, you'll get even higher. So unlike when you normally play guitar, you start up at the neck and then you go down this way, you get the higher notes. Actually, when you do harmonics, you start in the middle and you go up and you get higher notes. And if you ever want to see like YouTube videos on that, there's some people who can do amazing things with that. But anyway, it's just a side story. But molecules vibrate, okay? So they wiggle. There's all kinds of wiggles that they can do. They can do See, this is why I'm not recording video. They can do things like this. Like if I'm a methylene group, like a CH2, right? And this is connected to a carbon, and my feet are connected to a carbon. And these are my hydrogens, because I'm sp3, right? So they're 109.5 degrees, exactly. And then I absorb energy. I don't just sit here. I have to do something with that energy. So it turns out like there's frequencies like this, and then there's like this, and there's like this, right? That's more energy than this. Okay? This is known as scissoring. So molecules can scissor, but that's not the only way they can bend. Okay? They can actually bend like this. So these are called bends because what am I doing? I'm moving my bonds. I'm not changing their length. I could rock. Right? So there's scissoring. Right? There's rocking. No, that's wagging. And then there's rocking. And is that the only ones? That's the only ones I can remember off the top of my head. It doesn't matter. They're all bends. That's the idea. They're all bending. They're all in about the same energy. And then there's stretching. Like I could stretch like this, or I could stretch like this, or I could stretch like this, or I could stretch like this, right?
Getting a good workout there.
Yeah, my arms are tired already. It's kind of sad. That's because I did it yesterday too, you know.
2 days in a row killed that.
Actually, writing on the board takes a lot out of my arm because your arm is always in the air when you write on the board. So yeah, the only muscle I ever have anymore is this one right here. Okay, so when all those energies are quantized, though, you don't think about that. Like when a molecule is bending, there's only certain energy levels, so certain frequencies of the bending of the molecule and certain frequencies of the bending, of the stretching of the bonds as well. These all can be represented as springs. So if you guys remember from your physics days, something called Hooke's Law. Hooke's Law has a force, all right, and a spring constant. Right? And you can do a lot of stuff with Hooke's Law in terms of dynamics and figuring out what frequencies are accessible to these different molecules. And we'll talk about that, but we don't need to know all the details of Hooke's Law and how it works. Okay, so real quickly, because this is important for understanding of the way the spectrum is portrayed, but if I gave you an IR spectrum, let me just draw it real quick. The IR spectrum would have an axis like this and like this, right? It's usually a box. And then we have percent transmittance over here. That's how much of the light is absorbed. And then what do we have at the bottom? You guys remember what the numbers are?
Wave numbers.
They're called wave numbers. You remember what the numbers are?
Like 3,500.
3,500, 3,000, 400, 500, right? Usually starts out around 400. And then usually ends around 4,000. So that's only one order of magnitude. So if you think about it, that's one order of magnitude in what we call the wave numbers. And those units, if you look at them more closely, are centimeters to the minus 1. Okay? Now, what is think about what wave number means. It's the number of waves, centimeters to the minus 1, so that's per centimeter. So it's the number per centimeter. So literally, when you say 4,000 wave numbers, it's 4,000 waves per centimeter. Okay, so these are relatively long waves. Like when we think radio waves, those are really long. But when we think light waves, those are actually nanometers. So these are actually in the range, it turns out, of microns. So 4,000 centimeters to the minus 1, if you wanted them in standard SI units, which are meters for wavelength, then what you would say is, well, I have, let's say 4,000 centimeters to, per centimeter. There are 100 centimeters per meter. So that comes out to be 400,000, per meter. And to do the wavelength, you just take the inverse of that. So the inverse of that is 1 over 4,000 or 400,000 per meter. So that ends up being 2.5 times 10 to the minus 6 meters. That's about 2.5 micrometers. Well, it's actually exactly 2.5 micrometers. So that's actually the range of wavelengths that we're looking at. It's in the micrometer range. And we often call them just microns just because it's easier to call them microns.
What is this 100 centimeter over meter?
Oh yeah, it's just a conversion, 100 centimeters per meter. Yeah. Okay, so this is 2.5 microns. These are actually longer because think about this. 400 wave numbers means there's 400 waves per centimeter. So there's actually longer waves than 4,000. 4,000 is 10 times shorter than 400. Okay. Now, so let's talk about this spectrum, 4,000 to 400. In terms of wavelength, which one's shorter now? The 4,000. And this one's longer. And then in terms of, you guys remember the relationship between wavelength and frequency? Which is higher frequency? Shorter wavelength, right? So this is higher frequency. It looks like I have Parkinson's when I write on here. Anyways, which one's higher energy? High frequency goes with high energy, okay? So what we're going to have is energy is high on this end. This is low energy. So on the spectrum that we're looking at, this side of the spectrum over here, that's high energy, and this side's low. Now, remember, this relates to the photon that's absorbed by a molecule. So if the photon that is absorbed is higher energy, right, that means the energy transition of the molecule is higher energy. So let's say you had a double bond versus a single bond. Which one is going to be higher energy transitions, do you think? Double bond. Double bond, because it's a stronger bond, will have higher energy transitions. And as a result, on a spectrum like this, you would expect it to absorb energy at higher wave numbers. So in fact, stronger bonds are on this side, and weaker bonds over here. Now this is a generalization. I'll show you some stuff from Hooke's law that says it's not always just that way. But for a given set of atoms, like 2 nitrogens or 2 carbons, like a single bond versus a double bond versus a triple bond, that's the trend. Stronger bonds are on the left, weaker bonds are on the right. So far, so good? Okay. So electromagnetic spectrum, I'm going to skip this. So we're talking about infrared spectroscopy. I just want to point out to you the other kinds of spectroscopy that we may have some dealings with this semester. For sure, we'll talk about NMR at the end. That's nuclear magnetic resonance spectroscopy, where we actually rely on the energy for flipping the spin of a nucleus of an atom. Now, you guys remember electrons have spin, right? They either spin up or they spin down. It turns out nuclei have spin as well. So nuclei, depending on the number of subatomic particles, have spin. Turns out hydrogen is one of them. So we can excite the spin states of the hydrogen atoms in an organic compound and tell what their chemical environment is like. We can tell like what kind of atoms they're next to. Okay? IR spectroscopy has to do with really telling us about the energies of the stretches and bends of a molecule, but it turns out it's really good at telling us what kind of functional groups are within a molecule. And that's the kind of information that you'll be presenting like in your reports. You'll take your molecule and look for the frequencies and energies, I should say, of the stretches and bends associated with different functional groups. Like double bonds and single bonds, triple bonds, carbons bonded to hydrogen, those kinds of things. And UV visible is really good for conjugated pi systems. Okay, so a lot of dyes are conjugated pi systems. UV visible, UV vis, right? Visible and ultraviolet. Turns out when you have a lot of pi bonds, double bonds next to each other, they absorb light in the visible range. So that's why a lot of textiles, when you see the colors of the dyes of textiles, are actually organic compounds with pi bonds in them. We're going to deal primarily in this chapter with infrared and mass spectroscopy. So let's skip this. I talked about this, rotational, vibrational, blah, blah, blah. Hang on. I just want to get to the pertinent information. Oh, this is kind of interesting. Infrared light is heat. So when I say, like, okay, so you go to the fair and you're going to eat some of that really good food that they have there. It's always hot. You don't know when they made it. It's always hot. Why is it always hot? They put it under a heat lamp. A heat lamp is emitting infrared radiation. And when it emits infrared radiation, when something picks it up, when the molecules vibrate and bend, and that's heat. So they use a heat lamp. It's using an infrared source to generate heat. It also turns out this is actually a breast scan from one of the techniques that's sort of semi-questionable, semi-accepted, is actually tumors grow at a faster rate. They generate heat. And one of the non-invasive ways that they've been trying to come up with for looking at breast cancer, since this is Breast Cancer Awareness Month, is to use, if you didn't know, that's why I was writing in red.
Pink.
It's pink, but yeah. It was actually pink, it just looks red. Yeah, dark pink. So, but anyways, is to look at thermal imaging to detect the growth of a tumor. So that's actually what that's showing in that image, is showing a tumor on the right side of that woman's chest. And you can look this up, there's a lot of stuff on it. Okay, so, but that's just heat. That's what infrared radiation is, it's just heat. Okay, so, skip this. So infrared spectroscopy, what we're going to end up doing is we're going to end up taking infrared light source, passing it through a sample. Frequencies that are absorbed by the sample tell us the types of bonds and then therefore functional groups. All right. We measure, it doesn't really matter how we measure the frequencies that are absorbed other than we look at the transmittance. That question has a very detailed answer and a very not so detailed answer. So if I'll do it on here. If I make, hang on. I want to do this. If I look at an IR spectrum, there's percent transmittance here. There's wave numbers here. It's usually given a symbol like that. Nu with a tilde at the top. Okay. I'm going to get a signal that looks, there's 100% here. There's 0% here. If the signal looked like that, that would tell me no light got absorbed. 100% transmittance means I took a sample, I shined infrared light at it, the light didn't get absorbed. And the reason I know that is because at all the wave numbers that are present in this spectrum, it's 100% transmittance all the way across. Okay? So that's what it would look like if nothing got absorbed. Now, if it does something like this, okay, that would tell me, this is usually about 4,000 over here. This is usually about 400 over here. Okay. It would be just below 4,000 wave numbers that about 50% of the light got absorbed. I would know the energy that was absorbed by this frequency here, and I would know the amount of light that I got absorbed by the value that I get there. Okay? So there's two basic ways, and there's actually more, but there's two basic ways that we characterize the light that's absorbed. It's its energy in terms of wave numbers, and then the amount of light that gets absorbed in terms of whether or not it's 50% or 100% gets absorbed. Okay? So 50% transmittance would mean half the light got absorbed. Let's say it did something like this. Let's say this is a... What would I say about that one? All the light got absorbed. That's actually something you don't generally want to happen. It just means you have too much sample on your plate. Okay? You have so much that it absorbed all the light. So you generally don't want it to be 100%, but you want it to be close. So 100% of the light got absorbed at about 2,000 wave numbers. So those are two things we would use to characterize that particular peak. We would often say that this one's strong, and this one is probably medium because it's right around the middle. So we actually characterize it as strong, medium, and weak. I'll tell you about what absorbs strongly and what absorbs weakly in a little bit, but generally speaking, those are one of the things that we'll do, and then we'll also do it by wave numbers. Now, we can also characterize them as broad or narrow. Those would both be sort of middle of the road. Narrow looks like a little tiny sharp peak, and broad is what we saw for alcohols. I don't know if you remember the alcohol peak earlier. Eugenol. It's really like this. It goes about 400 or 500 wave numbers easily at its half height. Okay, so that would be broad.
What's the significance of broad?
Broad actually has to. Okay, so first of all, two things. Let's talk about small, medium, and weak. Small, medium, weak has to do with two different things. How many of those functional groups there are. The more of them, more strongly absorbs. Also has to do with the polarity. The more polar a bond is, the more strongly it absorbs. Okay? And then weak would be something that's not very polar, or there's not very many of them. Okay? So that's one thing that it tells us. The wave number tells us how strong the bond is, how much energy it either takes to stretch or bend a bond. Okay? Now, let's say, give you a couple of different scenarios. And let me just focus in. This is not any particular compound, but let's just say that's 2,000. And let's say the peak looks like this. Okay. What would that mean? Well, it means this represents the energy that it's at. It's a pretty, oh, sorry, I drew it upside down. I did it, sorry, long story. I'll show you over there. You can make it look like that. It's like click a button and it'll look just like I just drew. So let's say you have that. That means at 2,000 wave numbers, right, I had a fairly strong absorbance, probably something that's really polar, or there's a lot of them. That's what it means. Okay. The fact that it's narrow means that the bond strengths were all about the same. Okay, or the vibrational energies were all about the same, which implies that the bond strengths are all about the same. When a peak gets broad, okay, so narrow, let me put that in a little note. Similar bond strength. I wish I had my wife's handwriting. It actually, when she writes, it would actually look like narrow, similar bond strength. It's like all my drawings, I have to explain them because nobody understands what I drew. Okay, so that's what that means. let's say instead it was wide. Oh, and it can be this way. If there's one of them, it's only similar to itself. It's supposed to be really narrow, right? Can be that way. That's one of the things it can mean. But let's say it looks like this. Same graph. Right? If it's just one functional group, it could mean there's a very broad, even though there's one of them, it could be a very broad distribution of bond strength. So like the alkane peak, we'll talk about the alkane peak a lot later. It's pretty broad usually. The reason it's broad because the the CH alkane, the sp3CH, is usually pretty broad because the bond strengths vary over the molecule quite a bit, and there's lots of them, so that's what makes it wide. But it turns out like an alcohol will do this if it's hydrogen bonding, and we'll talk about that, just because the bond strength in the hydrogen bonded atom varies a lot. And we'll talk about why it varies a lot in just a second. Okay, so that's what the broad means.
So the broad means variable bond strength where the narrow means
Yeah, lots of different bond strengths or variable bond strength. Narrow means a similar bond strengths, narrow range. Tall, how deep that peak is, right, is telling you how polar the bond is or how many there are. There's a lot of different kinds of interpretations, but those are the general interpretations.
So you said that the eugenol had a really wide, so that would be very
That
bond
was
strength.
alcohol.
That was the alcohol,
Change bonding.
if it's hydrogen bonded. Right? You see that in the liquid state a lot or with concentrated materials. We call neat materials. Neat doesn't mean like it's tidy. Neat means it's pure. So if I have a pure liquid and it has an OH group in it, it's going to be hydrogen bonding to itself a lot. And so you'll see that in the IR spectrum. But if you take that same material, you dissolve it or make the concentration really low somehow by putting it in something else, then it can't hydrogen bond to itself. It turns out the peak will get narrower and it shifts to higher bond energy. Yeah. So I'll show you that. Okay. I have some examples of that in the slides. I have the slides I posted. I'm just using like bits and pieces out of it as I do the lecture. Okay, so just some examples, right? This is from 100 to about 10, so about 90% of the light is absorbed out on that one. That would be considered to be a broad peak. It's probably a hydrogen bonded OH. And this peak is the CH that we're usually looking at for saturated hydrocarbons, things that don't have double bonds. And there's a bunch of other peaks in there. This is probably the CO bond, but we'll get to all this stuff. That's generally, we've seen some IR spectra. I don't have to show you a bunch on this. We can interpret this one later. Okay, so let me skip through some of these. Okay, so this is an equation. Boo. Yeah, where they get the wave numbers. F is a force constant, bond strength. M is the reduced mass. Okay, so let's just do this little experiment. Well, actually, let's just talk about it real quick. If the reduced mass is higher, what happens to the wave numbers? Look at the thing. If the reduced mass is higher, and reduced mass is this product of the masses divided by the sum of the masses. That's a physics thing, okay? If this reduced mass is larger, don't worry about what the numbers are over here, but this M red is bigger, then the wave numbers get smaller, they get lower, right? So if something has a large reduced mass, and I have an IR spectrum, is it going to be closer to 4,000 or 400? It'll be closer to this end, right? To the 400 side. That's what you expect. The force constant is literally the bond strength, okay? So, let's just do this thought process. Let's say I have a carbon bonded to a hydrogen. And let's look at the reduced mass. This is 12 times So M red, 12 times 1 divided by 12 plus 1. So what does that come out to be? Comes out to be around 1. Right? Because it's going to be 12 divided by 13. Let's say I do C bonded to O. Okay, so, oops, I started that too high. That's going to be 12 times 16 divided by 28. And what does that come out to be? Let's just do the math real quick. Because sometimes it's best to prove things to ourselves just by seeing it. 12 times 16, oops, try 12, divided by 28, 6.8. All right, so, oh, sorry, 6.9. Doesn't matter, I rounded wrong, but it's 6.9. So the reduced mass is larger, the bigger two objects are. Okay? So heavier atoms, larger reduced mass. Where do you expect to see them? Further to the 4,000 side, or closer to the 400 side? Closer to the 400 side because they're bigger. So that's why when you see like CH and CO, right? If you guys remember from the IR spectra that you had before, this is the CHs. That's why they're so far over here. This is the OH, right? Again, the reduced mass is close to 1 for OH. And then C double bond O is typically over here. Carbon to oxygen, two bigger atoms, is more to this side than to that side. Okay? More to the right than it is to the left. The stronger the bond, the closer it is to the 4,000 side than the 400 side. And if you remember from the bond energies chart, all the bonds to hydrogen are typically higher in energy. So bonds to hydrogen typically end up on the left side. That's why we're seeing them on this side of the graph. That's where the CHs are. Okay? And the OHs. OHs are way over there because the bond to the hydrogen is typically stronger because the hydrogen's smaller and it makes stronger bonds. So just some examples. This is known as an isotope effect. By making it deuterium, it changes the reduced mass a lot as a percentage, and so you see this big difference in like wave numbers. But CH, right, 3,000, CO, 1,100, CCl, 700. Okay, so that's an effect of the reduced mass and the bond strength. They both kind of change. If you look at CN, you could have it as a triple bond, as a nitrile, as a double bond, or as a single bond. And you'll notice, same atoms, same reduced mass, right? But because the bond strength is getting stronger, these are for stretches, okay? You'll see it go from 1,100 to 2,200 wave numbers. So you can tell, like if you look in a spectrum, you know you have nitrogen. If you see a peak at 2,200, you probably have a nitrile. Okay? That's the part where we're, take an unknown and try to figure out what you have. That's when it becomes useful because you look at all the possible functional groups that you could have. You're usually given some empirical formula information. Like if you get a real unknown in this class, I'll generate a mass spectrum. You'll know the molar mass of the compound and you'll know its elemental composition as well.
So does that hold for like any triple bonds are going to be a larger?
Yeah, any triple bonds are further to the left. So like triple bonded carbons, alkynes, you expect to see them far to the left. So let me show you something real quick. So this is a sort of a general useful table, but it's not super useful because it's too general. But anything bonded to hydrogen's way over here. Bond strengths are high, reduced mass is low. Single bonds tend to be in this region. Double bonds tend to be in this region, and triple bonds tend to be in this region. Okay? So we see, in general, an increase in wave numbers for higher bonds and also for stronger bonds. Now, diagnostic region. What do you do when you make a diagnosis? You look at the data and you make an initial diagnosis. You just, of course, they got a hole in their head, they're bleeding. You kind of know what it is. But you look at the symptoms and you make a diagnosis, initial diagnosis. That's actually what this diagnostic region is used for. You look at this region from actually I usually use from a little lower than 1600, but it doesn't matter. I usually go from about 14 or 1500, and then I go up. That's my diagnostic region. I look at it and I can very quickly tell, oh, these are the functional groups that I have in my molecule. Okay? I don't know much else about it. I just know initially these are the things that I have in it. The fingerprint region has a whole bunch more information. Okay? Now, if you remember, let me go back to some spectra. Let's look at a spectrum anyways. All right? This is 2-butanol. Again, a favorite compound because it's chiral, or can be chiral. OH, that's your OH. CH. All right? And then a whole bunch of other information. There's so many peaks in here, you can't tell like exactly what you have. But because I know I have an OH, I'm assuming that's a CO. That kind of stuff.
So all the CH bonds are represented by that one peak.
By that one peak, but because some of them are bonded to this carbon and some are bonded to this one and this one, they have different energies because they're primary, secondary, and this one's attached to an electronegative group. They're going to have different energies, and because they have different energies, the peak tends to be broad just because they have different energies. And there's a lot of them, so that's why the peak is big. Okay?
In the CH region, like in the book, it talks about aliphatic and aromatic.
Yeah, we'll get to
so
that.
that's-
Yeah, we'll get to that. Okay, so what the fingerprint is used, like so let's say I committed a crime and let's say my fingerprint was on file, but I think my fingerprint's only on file because I had to be screened a couple of times for different things.
Sure.
Yeah. No, actually the coolest one was when about 6 or 7 years ago, I did a summer internship as a professor, and then I had to have like a security thing. They did an eye scan and a finger scan.
Live scan.
So now if I shoot somebody, my fingerprint's on file, and they find a fingerprint on the casing, because that's the thing they always leave behind, right? Find a fingerprint on the casing, what are they going to do? They're going to put it in a computer, and they'll try to match that fingerprint to people that have that pattern of lines on their finger, right? They can't look at the fingerprint and say, oh yeah, that's Kirkagua. Right? Man in a black hat. But they'll look at this, they'll match it using a computer algorithm to be able to identify. That's why it's called the fingerprint region. There's so much information in there. They match the shape to a library of information. That library information tells them what compound it is. That's how that program that we use in the back in the IR gives you that percent match. It's the percent match usually in the fingerprint region and a little bit of information that's out here. When they have impurities in like medical materials, medical grade materials, a lot of times it's identified by IR that there's an impurity because a lot of times you can see automatically, oh, there's like an unusual peak in that region. It's an impurity, we need to throw it out. Okay, okay, so all right, you probably wouldn't be able to tell which of these two is 2-butanol versus 2-propanol. They're both alcohols, they're both aliphatic, they both have CHs in them. The fingerprint region is very complicated. You could kind of tell, oh, relative proportions, whatever this is closer to the proportion of this just because, right? It's shorter here and taller here. There's really not that much more information in there. Your book might say otherwise, but I'm just going to say practically speaking, we don't do much with that region. Okay? There are a few things I tell people, oh yeah, you can look in here and you can find some interesting information. Usually in this region, like here's 1400. If you get a peak here and a peak here, right to the left and right of 1400, that's usually a methyl group. Right, it's a methyl bend. But like even on that one, it's not very clear, and basically it's just two methyl groups and a alcohol. So you know it's not useful like the OH is useful. The OH, which is over here, oh yeah, that's OH. Okay. Okay, now here's another interesting thing. So when we say aliphatic and aromatic, okay, or vinyl, that indicates the type of pi bonding we have in a system. And we're looking at aliphatic, that just means sp3. Okay? Vinyl or aromatic is sp2, and then alkynes are sp. So it turns out, if you think about it, when you have sp3, when you have sp3 orbitals, right? They're actually longer than sp orbitals. sp3 orbitals are longer than sp orbitals just because p orbitals are long, s orbitals are short. So as a result, this bond is shorter. You expect to see it at higher wave numbers. Because it's a shorter bond, it's stronger. Same reduced mass. Okay? Now, this one, right? sp2 versus sp3. This is the one you have to be very rare. Alkynes, we don't see them that often. I mean, they're definitely biologically active alkynes and all that kind of stuff. Okay, but we don't see them very often because most of the time they're not terminal. They're not at the very end. And the only way that you can have a hydrogen on an alkyne is if it's terminal. On the other hand, alkenes we see a lot of. So this is a vinyl hydrogen. This CH ends up at 3100. This is what they look like. So this is what it looks like when it's sp3. This is that grouping that we saw earlier. It's between about 2850 or 2800 and 3000. But it turns out if you have a vinyl hydrogen, a CH, it'll be just to the left of the group. So you can see this peak, then you're pretty sure you have a double bond. If the peak is even further over, so this is just to the left, and again I say you don't usually see these that often. This is all the way out around 3250, 3300. That's the CH for a triple bond. Okay? I was going to load up a bunch of spectra, and this is probably a good time to say this. You're going to need to look at a lot of spectra. Okay? Great websites. Let me write them down for you. Probably should have said it at the beginning. I'm not going to give you these in the order I prefer to do them. I'm going to do them in the order that they're available right now. So, Japanese spectral database. Google this. So let me just say this. I don't remember the actual link, but that's how I find it all the time, and you'll see ROBI. I'm pretty sure it's the Japanese national database. It's a research database. You can find all kinds of IR spectrum in there. All you need to do is type the name in or the formula, and it'll spit it out. Okay, it's very nice. It'll also do mass spectrum, NMR spectroscopy. It'll give you a lot of physical constants and information about particular compounds. Okay, so it's a really nice database. That's one of my preferred ones. The other one is a company called Sigma Aldrich. They sell all kinds of stuff, but when you go to the Sigma Aldrich website and you search a compound, under the reference material for that compound, they usually have IR spectrum, mass spectrum, NMR spectroscopy. Now, one of my favorite sites is the National Institute of Science and Technology, NIST. The problem is, it's closed. Because they're government, and they closed it. And apparently it takes somebody in the government to run the server or something, but they closed it. As soon as the government closed, they shut it down. Like, poop heads? That's all I said. That was not what I said. But that's the 4-year-old version of what I said. So, yeah. But normally, again, you put in information for a compound, it'll give you all the thermodynamic data about the compound. It'll give you IR. It'll give you NMR. It'll give you UV visible spectroscopy, sometimes mass spectroscopy. It'll give you infrared spectroscopy in multiple different solutions. It gives you all kinds of stuff. Closed. So, having said that, we'll just move on from there. But yeah, that's a great website. I haven't tried going to it today, but that's normally what I do is I pull off a bunch of compounds and I throw them on the slides and I talk about it. I have some old slides, I just didn't want to use them. Okay, so let's talk a little bit more about how IR signals can be changed. It's a little hard to predict some of this, I'll be quite honest with you. But this is where you expect to see a ketone. Okay? 1700. And it's going to be a big peak because it's related to the electronegativity difference of the two atoms. CO is a very polar bond, and in one of its resonance contributors, it has this. Okay? And that causes this bond to be a lot more polar than we normally expect to see it. So that's a very big peak. It's usually right in the middle of the spectrum, around 2000. It's actually around 15 to 1800. Okay, but this one's at 1720 in particular. If you put a double bond next to it, right, it shifts to, is this higher or lower energy? Lower energy than the parent, right? What's the difference? Well, let's think about that. Let's go back to the last slide. Remember resonance contributors, right? If I put a double bond here, then this can resonate over here. The percentage of the time that the molecule spends with this bond as a single bond versus a double bond goes up, and as a result, single bonds are weaker than double bonds. A big shift to the right in terms of its strength. Similar, if this is the parent compound, and you put a double bond next to it, it shifts a little bit. Just because one of the resonance contributors that becomes more common is the one that has a single bond between the C and the O. Oh, by the way, why does polarity of a bond affect how much light it absorbs?
It's a stronger bond, so the molecules are much closer.
No. It's actually kind of abstract. It's not something I would expect you guys to think of first off. When we talk about light being part of what spectrum? It's the blah, blah, blah spectrum. Electromagnetic spectrum. So actually, when light is passing through space, it's going through the electromagnetic, it's going through an electromagnetic field. And we don't see it, okay? But when light is traveling through this medium, it's creating oscillations in the electromagnetic field. Now, we think of electric fields as being pluses and minuses, right? So the electromagnetic field is going up and down in terms of its potential. If you put a polar molecule, a really polar molecule, in an electromagnetic field, it's going to respond to the oscillations in the electromagnetic field. If it's a nonpolar molecule, it doesn't have any charges on it, and the electromagnetic wave goes past it, it won't absorb it. So it has to be polar or somewhat polar for the electromagnetic radiation to be picked up. Okay? Or polarizable, I should say, is probably the other thing too. Okay. Talked about that. Talked about that just now. All right. So, all of these things are oh yeah, hydrogen bonding. So that's the last thing I want to go over. Then I'm going to talk about the kinds of things I want to see in reports. Okay.
Oh. How many have we turned it on?
Yeah, no, that's okay.
Doing it wrong.
Up till now, it's sort of been trying to get people to get the idea of how they're collected, put them in your documents, try to analyze them, and then I'll tell you like what I want you to analyze. Okay.
Do you want notes from this lecture right now and put in our lab book?
Doesn't have to be.
Might be helpful.
Would be helpful, yeah, some of it, some of it would be helpful. In fact, most of the time when I give you things to do in lab, even if it's a lab practical, like at the very end, I let you use your lab notebooks.
Yeah.
I'm planning to do some lab testing in the second half of the semester. Not a lot, but yeah, you can use your notebooks when you do that.
This could be heavy.
Wouldn't hurt, yeah. Okay, so I'm going to draw a picture. Stretch my arm. Here's an OH. Okay. And OH can hydrogen bond. Pair of electrons. Now, how many bonds can a hydrogen have? One. So when the hydrogen bond forms, what happens to the strength of that bond? It gets weaker because it can only have one bond. A hydrogen bond is the beginning of the formation of another bond. Like in an acid-base reaction, this would come in and take this, and that bond would break. Okay? If that bond gets weaker, right, you expect it to shift to the right, because this is weaker. Over here on the right at 400, 4,000 is stronger. So this is a pretty strong bond just to start with. But then if it has hydrogen bonding, then what happens is that bond becomes weaker. You expect it to be shifted further to the right. But here's the thing. If you're hydrogen bonding in solution, this distance isn't fixed. These molecules are constantly moving around. This distance constantly changes, and that means this strength constantly is changing. So where you would expect normally a narrow peak, way over by like 3,700, I think it is. Okay, it's usually over to the right and much broader. Okay, so to see that, you just need to look at a spectrum. This is the free OH. That's the non-hydrogen bonding OH. Now the way you get that to happen is you just separate the molecules from each other. Okay, so like if you ran a gas phase, that's the gas phase IR spectrum, all you would see is one really sharp peak. But in solution, or in the liquid form, when they're close to each other, you get this much broader peak because the strength of the OH bond changes a lot. Okay? Free OH to the left, hydrogen bonding OH to the right. The more interaction that occurs, the further it can shift to the right. In carboxylic acids, there's a lot of hydrogen bonding that goes on. So when you look at the OH in the carboxylic acid, it's usually right on top of the CHs. Just makes it's a big mess. You know you have carboxylic acid because the IR spectrum is so messy. All right, you're gonna have the big around 1600 peak for the C double bond O, and then this peak's just a big blob usually right in here. But that's because carboxylic acids do a lot of hydrogen bonding.
Is that peak to the right of the OH and hydrogen bonding still hydrogen OH, or what is that?
Oh, this? These are just CHs. Yeah, you almost always expect to see CHs just because it's organic chemistry and there's a lot of CHs. When you don't see it, then that's significant. Like if there's a peak, like a CH missing, you're going, there's no CHs. All right? Or they're all aromatic and they're all shifted over, that kind of stuff. Okay. Yeah, so that's a carboxylic acid. All right? This is the big messy peak. This is the C double bond O for the carboxylic acid, and this is the OH because of all the hydrogen bonding that occurs. I think they have a picture of that. Yeah, that's what the hydrogen bonding looks like in a carboxylic acid. They bond together, and that strength of hydrogen bonding causes that peak to be really
So
messy.
that funky little like thing at the bottom, right above the 3,000, those would be your CHs.
Those are your CHs, yeah.
Okay.
These are CHs, but they're now buried by the OH. Okay. Let's see, what else do we want to... Oh, yeah, so the last thing is just to talk about what needs to be in reports. We definitely have to have the IR spectrum. Should be in your notebook, too. So I'll make that note. The other thing that you're going to do, and how you analyze it, okay, you should make a table. Now, it doesn't have to be a table, but I say you should make a table. I'm going to show you two different ways to do it. Some people love the table. That's normally what goes into scientific journals, is a table. They don't usually show spectra, unless there's something really unusual about it. But a table. So let's talk about the table. So what you'll have in your table is headers. They don't have to be in this order, but this is typically how people do it. You need the wave numbers. The wave numbers are arranged. It's like the melting point, where it starts, where it ends. Right? And then I want a description of it. So description.
You want the actual wave number from our own IR spectrum?
Yeah. And like the approximate range. Okay. So description would be strong, medium, weak, narrow, broad. Yeah. Broad. There we go. And then the functional group. Well, it's supposed to say group, but it doesn't really look like group that much. That's a simple table. You might put other things. It doesn't have to be only. Like I said, it doesn't have to be in this order. You put functional groups. You could put the wave numbers and the description. I don't care what order it is, but that's generally how it's done. The other thing you can do, which I really like, and this you can do both. In fact, in your notebook, this is probably the way you'll end up doing it. Spectrum. Huh, what do you think that is? Got an OH group. It's got CH3s. Oh, let's do this. Got this. Yeah, it might have C double bond to O in it, but it's not a carboxylic acid. Let's say there's a peak there too. Right, this could be a C double bond O, but it's really narrow. Remember, this could be C double bond O as well, but it wouldn't be a carboxylic acid because it was a carboxylic acid. This one would be stretched all the way out over here. Right, so we know that it's probably got an OH. It's probably got a CO in it, and then I'm not sure what that is. Maybe a triple bonded something or double bond, because I don't have any numbers down. I just made up I just drew squiggles, right? So, but you could guess like this could be a double bond on something. Okay? Normally it wouldn't be that big, but that's kind of guessing. Then what you do is you draw your structure. Let's say your structure is this. I don't know what that is. Just made up something. There. Looks like a little man running. His hands out. I didn't put a head on him, but right. Then you could say things like that. Just in your notebook, like when you're taking notes, you know what, because normally you know what the product is, right? So you find the functional groups on your product, and you look for where you would find it in the spectrum. And then when you go to type it up, then all you do is you look at what you did in lab, and say, oh, that's that, and you just type the wave numbers on and the description of the peak.
So we can just put a copy of the IR spectra in there,
Yeah,
put that structure there, and then just.
yeah,
draw
in your
arrows.
notebook and draw arrows to it. And then if this really had a benzene ring in it, it would have a bunch more peaks in here that were paired and all that stuff. Best thing to do is go into your book, your lab book, and in the back they got pictures. And so if you think to yourself, gosh, what does the benzene ring look like? Well, look in the back of your book. It shows you what a benzene ring looks like and where the peaks are. Okay? So then you can identify them. And that's for this semester. This semester mostly is you're given a compound, you make it, okay? And then you go to it and say, oh, I made this compound. What are the peaks supposed to be? In the future, what happens is you make a compound, you're not told what you're starting with. So you end up with a compound, you take the IR spectrum, you go, oh, gosh, what functional groups are there? Oh, what was my starting material? What's the reaction? You know, that kind of stuff.
So do we need to do every single peak, or just like?
No. Just like I did here. I picked the major ones, right? And like I said, if there was, I didn't put the benzene rings, but the benzene rings would be like pairs of peaks like this. You often see these peaks in there. That would be the benzene ring.
Yeah, in the book it says like to confirm if you have an aromatic CH or whatever, to look between like, I think they said 14 and 1600
Yeah.
for like several peaks. Like
Yeah, now there's a whole table in your book. Okay, one of the things that's really cool about benzene rings, this substitution pattern it only has certain vibrational patterns that are available to it. It'll create a if the area is clear, it'll create a pattern of bumps that you could diagnose to tell that they're all at 1, 3, and 5. Okay. Or if it's 1 and 4, you'll see a series of bumps. Or if it's just one substituent, you'll see a series of bumps that tells you it's just one substituent. Yeah, it's like phrenology. You know what phrenology was? Where they would read the bumps on somebody's head and try to predict like what their life and future would be like if they were smart. It happened around the early 1900s. So this is like phrenology, right? You're looking at all the bumps and you're saying, oh, I think that's what this is. Your future is bright. You're a benzene ring.
And the book doesn't explain it very much, but like it does like let you know that you can determine like where it would be, where the substituents would be located on your like aromatic ring.
Yeah, and the thing that you'll want to look for, let me do this real quick. This is what you'll want to search. It's an IR, because your textbook doesn't have a very good one. Most books have a big one in the back. It's known as an IR correlation table. Okay, so an IR correlation table will actually show you like functional groups and where you expect to find peaks. And the big ones are pages and pages and pages long. The one in your lab manual is only like a page and a half. Your textbook doesn't have one. It's one of the recommendations, hopefully, that gets put into the next edition. Yeah.
I know with the last lab we had, there's like an overlap of like the NH group or whatever with the alcohol group.
Yeah, there's all kinds of weird things in that one, yeah. So, but from now on, this is what you do. Table for the reports. You can put really, if you do both of these in your report, that's great. But this should be in your notebook. The one on the right should be in your notebook. The one on the left should be in your reports.
When are you going to look at our notebook?
Soon.
Are we getting any reports back?
Yes, but not yet. This is all common questions, I know, but that's all I